This is the Empower Podcast. Released February 20th, 2023. Episode 620. Engineering Education with Dr. Don Wilcher. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
And I'm Dr. Don Wilcher of Maydon Research.
Hey, Dr. Don, how are you doing?
All right. And I like that name, Dr. Don. Either it's Dr. Don or Dr. D, but I like that. I was kidding around with my wife. I would like to get a cape so I could be like Dr. Doom, right? Just battling.
Well, I don't think Dr. Doom is the one. He was not.
Well, yeah.
I don't think he was the good guy, right? Right. Bringing engineering mischief wherever you go.
Yeah, there you go. I'm battling injustice with engineering mischief, right?
Injustice and lack of constraints in a engineering problem.
Yeah, exactly. Yes. Right. What's the uncertainties, right? So yeah, exactly.
I have seen your name in my inbox on a pretty regular basis from the DigiKey and Design News, I think.
Yeah.
The continuing education courses for a long time. And I'm really excited to talk to you here. You've been doing lots of great talks and educational things. So I'm really excited that you're here. Can you give people an idea of like your interests and area of study that you like to focus on?
Well, my area of interest has always been electronics. That's my baby. But, I've been moving into the embedded sphere, prototyping hardware devices that can do industrial controls. That's Megatronics-based type development, robotic systems, really just putting brains into mechanical systems and improving their performance. So that's where my forte is, and really originated, working in the automotive engine or industry, I should say, way back when in like 1986 when I graduated from Wayne State University, which is a urban university in Detroit, Michigan.
Yeah, that's right. Yeah.
That interest was always there. Like I started off as a plant engineer working at a assembly plant, which is no longer in existence, called the Will Run Assembly Plant. And that's where I started to see how industrial controls work from a programmable logic perspective. And, I had those courses in college, particularly in community college, because I got an associate in electronics technology from Henry Ford Community College, which is a great college. They had a lot of great instructors, and those guys were like geniuses because they all had like master's degree. One had a master's in physics, one had a master's in electrical engineering, and another one's mathematics. So they really allow us to think on an engineering level, even though it was a 2-year institution where you got to associate, like you go out and be like a technician or maybe an engineering technician. But those guys really put that knowledge of analysis and thinking critically while I was getting the 2-year degree. And of course, I got, my bachelor's in electrical engineering from there. And that's when I got into the industrial sector, again, starting at Willow Run Assembly Plant and learning about embedded systems, but from an industrial perspective, meaning the programmable logic controllers.
Yeah.
And when I was taking that course at Henry Ford Community College, I couldn't understand the logic. It just like, I couldn't get it. They had some wonderful training systems that they built. They, say, hey, select a particular project that you want that will demonstrate how the PLC works in an industrial environment. So they had like pneumatic cylinders that you can select to say you're going to make this little pneumatic robot, or they had some motor driven like variable speed drive systems, but I could never figure out the logic part. And it clicked when I actually got into industry. It's like, oh, okay, that's what those guys were talking about when they looking at those ladder logic.
Seeing it like on the floor and seeing like being able to actually like move stuff and get like visual feedback and hearing things going right and wrong, that sort of thing.
Yeah, absolutely. And then, me being an instructor right now at Jefferson Community College, I actually taught when I was in Michigan, Lawrence Tech University. So I was working with mechanical and electrical engineering students. And it was funny, Chris, because every time I would step into the classroom, I say, hey, this is what we're going to do. And what we're going to do is make stuff. Okay. Like we're going to actually take what's in the book.
Yep.
And we're going to explore if it's, just traditional transistor amplifiers, op amp circuits, 555 timers, even, like low levels, I call it, power supplies, linear power supplies, looking at half wave, full wave, or, full wave bridge. They had a kit, and I would actually write these labs, and they thought it was like I was like some mystic person, because
Hmm.
all
Oh
of them
yeah.
would say, "Man, this is what we've been wanting to do."
Yeah. I remember in my university, like, they had all of these very fancy mathy courses, but the one that hit, and I was just talking about this, Larry Sears, when he was on the show. He was the first one of two guests who ever was at the my Cleveland basement recording facility. This is a man who donated many millions of dollars, and I invited him into my basement into Cleveland, and he graciously accepted. Yeah, he had the best course where it was just teaching out of like art of electronics and hands on, that sort of thing, and people still talk about. I mean, like, it's just like it's the core. So I'm sure you are the Larry Sears of Jefferson there. Yeah.
Yeah, and it's sad, Chris, that universities have moved away from that. Like University of Alabama, I've been having conversations with them because I'm trying to, formulate this relationship, a bridge program where anyone who gets a 2-year degree
Oh
can,
yeah.
move on to get a 2-year, say, engineering technology degree, and therefore, but there's a lot of politics, unfortunately, in
Yep. Yep.
post secondary and higher ed. So we have these conversations, but the key aspect is for me, if you're going into engineering, if it's mechanical, electrical, chemical, you should be making stuff.
Totally.
And we've lost that as a society. Kids don't
Yep.
know the joy of making stuff anymore.
Right. Yeah, and I think that's a really interesting point about the joy. I was gonna like be like, oh well, the practical nature is like, well, you want to like show up and be able to show up at a job interview and all this other stuff, but there is also like just the, I don't know, like that's a really good point about the joy, because there's so many other things that people can do these days, right? There's so many other paths to making money and even interesting technical problems. And like, if you don't have that joy, how are you gonna get people to stick around and like stick it out through the bad math sessions and stuff like that?
Right, and I agree, and you're bringing up a good point about the lower bad points. For me, and we're all human. I'll have my moments like, I'm trying to think of like a project, and I got like tons of notebooks around me. I'm even looking at some of them where I go in and find a page, and like, oh, I get inspired, right? And then from there, I'll go into my creative mode. There's two ways I can do it. Either I can kind of, like sketch out the concept like a system block diagram, and then from there, I'll go ahead and, design the circuits,
Hmm.
not get into the analytics. The analytics really come for me when it doesn't work. And then I'll
Hmm.
say, hey, I'm going to either do a model, some circuit simulation model, or I may do paper analysis, as I call it. But the real aspect of engineering is the making stuff, like because the parameters are going to change. Environmentally, conditions are going to affect, like how transistor work, for
Oh,
example.
sure, sure. Yeah, like, what is that? Was it Patton? It was like, no plan survives the contact with the enemy, or no
Yeah, yeah, exactly,
no
right.
lesson plan survives contact with the real world and the breadboard.
Right. Exactly. Exactly. And that's the whole thing. I mean, when I found out about breadboards, oh man, that was like heaven to me because
Hmm.
it opened
Yep.
up so many possibilities. I mean, I got exposed to this whole making thing, and I'm gonna say I think I was like 4 years old. And it was
Hmm.
strange, Chris, because there was a radio that was
Mm.
like not in a case. It was just a printed circuit board. I didn't know what it
Yeah.
was,
Yeah.
but I thought it was like little people actually,
That's
talking,
great.
playing
Yeah.
music, right? But when I saw
Yeah.
this radio, it's like, well, there's no little people. So what I did was, and it was like a perfect storm. It was like, somebody say, hey, this is your pathway. There was
Hmm.
two wires. It was a red and black wire. And I knew that that little device needed power. So guess what I did? I plugged the red wire and the black wire into the 120-volt outlet, and smoke came out. And
Uh-huh.
I'm like, okay, where's the little people? Right. But that's what
it's
really inspired me.
It's funny. That's, like, it's the engineers they all have the same origin story, or some version of it, and yeah, you got the same origin story there. It's like I took a thing apart, or I blew a thing up, or
Right.
I, like, that's great. I love it.
It goes back to that Dilbert
Hmm.
cartoon where the mom takes Dilbert to the doctor, and he's constantly taking things apart, and the doctor said, "Oh." And she said, "What is it, doctor?" He said, "He has the knack." And the mom
The
starts
knack.
screaming, right? Right, right. She starts screaming.
The
Yeah,
classic.
it is. But that's the whole, like DNA for us, right? We
Hmm.
see the world differently and we want to understand it. So the only way we can understand it is we go in and we take stuff apart.
Hmm.
And that's where the knowledge starts to grow, right? The hands-on skills start to be developing, and one thing leads to another. And next thing you know, you got your own little lab. And I always had a lab. I mean,
Yeah.
just making stuff, right? Taking
Yeah.
things apart. Just I
Right.
got to have a lab to be creative, so I can learn how the world works.
Yep. That's great. I'd love to go back to the, so you mentioned like the industrial focus. That has a special place in my heart. I come from that space as well. And we've had other guests on the show, like I mentioned before we started recording, like John Davis, who works in that space. And we've had a couple other folks. But could you kind of just give us a rundown of like, I always kind of see PLC stuff and I've been around PLC stuff and, but like, what is the main operating mode of PLC? And then later in the show, I'd love to talk more about how people are moving between that world and kind of like the more programmatic world and where the crossover happens.
Okay. Well, PLCs, Dick Worley they call him the father of programmable logic controllers. And what he noticed was this movement that was happening in the industrial space where some of the tasks that, say, workers were doing, particularly like skilled workers, they were making controls and they were doing it using relays and switches and indicator lamps. But he thought it would be more advantageous if there was a box that, if you could take the physicality of the contacts of the switches and illumination of the lights, you can put it into this box and just basically use the knowledge that the plant floor technician electrician had, meaning like relay ladder logic. Okay.
Yep.
That's where the formulation of the PLC happened. People call the PLC an industrial computer, and if Dick was alive today, he would turn over his grave. He's like, no, it's not an industrial computer; it's an industrial controller.
Hmm.
But the fact
Okay.
that you have to have a computer where you put the software on,
Hmm.
that's where people kind of moved it to like, oh, it's a industrial computer, but that was never the intent. He wanted to make an industrial controller, a programmable industrial controller, and it was based on the,
How would you define the difference between the computer and the controller?
well, the difference is it has its own architecture,
Hmm.
and what you're doing with the laptop computer or the desktop PC is that's the interface where you can actually communicate with that PLC. Now they have handheld terminals,
Hmm.
and you can actually plug it into, say, a D9 connector, some type of serial port where you got communication. But the challenge with that is if you got a real long program, you don't want to be actually hitting the little symbols and constructing your ladder logic program. So the ideal of having a computer
Mm.
where it interfaces with that communication port and is talking directly to the CPU, it makes it more convenient because now you can take a mouse and you can move these little bit instructions, as they call them. They got timers, counters, and you can construct the logic faster, more effectively. And then you can save it. You can actually go back and open up. Not to say you can't do that with a handheld terminal, but the time to do that, you got to go through each rung, and then you got to find the bit instruction, and you got to select it and change it to whatever
Mm.
you want it to be. Yeah, that's the thing. So for me, I can see where they're saying it's a computer because it does have like inputs and outputs when you look at the modules in a rack. But the difference is the actual computer itself can do more than just doing controls. So that's where the controller comes in. It's like an embedded controller, right? You know about embedded
Got it. Got
systems.
it.
It's
Right. Right.
very task oriented, very specific, and all you're going to do is just hook up another means of interacting with it, a laptop computer or a desktop PC.
Hmm.
And
Yep.
then you can make your changes, and then you can download the program, or in this case, with the Arduino, you can upload it, and then you're off
Hmm.
to the races. And now it's running on its own, right? It's kind of like some semi-autonomous. It just runs on its own.
Yeah.
But then if you want to make changes, you can go ahead and do that. So that's what it means for me.
Okay.
It's a programmable logic controller, not
Yeah.
programmable logic computer. That's
Right.
that's the thing. Yeah,
Right.
yeah.
So like in a PLC, normally your programming ladder logic gets translated into some kind of machine language at some point, and then it just like it's running like a tight loop. Is that kind of the thought, or is it actually sequential?
Depending on how you program it, now it does have a scan loop.
Hmm.
So what happens is when you write, say, 3 rungs of instruction, it will actually go through 1 rung and then look at all the states of the bit instructions. So what I mean by bit instructions is that they have examine if open and examine if closed, or XIC and XIO. If closed just means that you're looking at when the switch is in an open state, the contacts, and it transitions to a closed contact, or in this case, like an event, then that's the examine if closed. Thus, you're examining it when it's closed. What's going to happen? If it's examine if open, now the switch is already in a closed position. So now you're getting into this inversion. So when you
Mm,
look at it from that standpoint, you want to see when the contact's open, and that's where your rung's going to be true, right? Even though it's like, wait a minute, that doesn't make sense because if it's open, it's not going to work. No, you're looking at the logic perspective, not
mm,
the functionality. The functionality is there because when you actually mount all these switches, even sensors, onto a specific machine, you have actuators, and the actuators are going to basically engage with those switches or sensors. And that's where the magic happens. So you have
mm.
to look at
Got
it
it.
from that standpoint when it's running, but also meaning like a dynamic standpoint, but or real time. But you got to look at it from the initial condition, like what is the state of the machine, and then what's going to trigger it to make it do some type of output response.
Got it. Could you give us an idea about like maybe the practical limits on what you would expect to see in a single PLC in terms of like the actual application? So like a conveyor belt plus a I don't know, a slicer in a food factory or something like that versus
Yeah.
like an entire car line. Like where does it fall? Like where you would start to split up into multiple controllers?
That's pretty interesting because they do have what's called distributive control systems, DCSs.
Sure.
And the
Yep.
ideal behind that is to kind of spread the wealth, meaning you don't want to overwhelm the main processor, like the microcontroller.
Hmm.
So the ideal is if you're going to do a distributed controller, it's pretty much like you have a remote, like a PLC that's at a remote station. So you got an
Hmm.
operator that wants to start this meat slicer, okay, that you described.
Sure. Sure.
So
Yeah.
they got a control panel, an operator's panel, and the meat slicer is distance away because we don't want that operator to get damaged, like hurt,
Hmm.
okay,
Yeah.
because
Right.
it might do something crazy. So you put that actual meat slicing mechanism distance away, and now that meat slicer will have a controller there on in this location, so you can network them, right?
Uh
Now
huh.
the ideal is by networking them, you're setting up this communication network, and it's sending data to and from the remote versus the distance controller. But the key is you don't have one processor that's doing all the work. You're distributing
Right. Yep.
the workload, if you will, like how it's going to be able to effectively work as one system. And that's
Right.
that's pretty good because again, you don't want to overtax that one PLC microcontroller where it's got to do multiple tasks, and that can kind of bog down the system depending on what that system is.
Hmm. Okay. Okay. What about like so like on a single controller now? So like you have one that's on the meat slicer, or whatever it is, and are there like kind of I don't know rules of thumb or similar like for like how many inputs and outputs it can handle, or is that more hardware dependent depending on the vendor you go with?
It's more hardware dependent because the way that works is you'll have a rack,
Hmm.
and the rack will allow you to actually put the various IO modules. You can put counters, you can put sensors. So, depending on your application, that's where you get into the design of the architecture, right? So, you
Got
do
it.
your
Okay.
system architecture and you say, hey, I'm going to have like 3 inputs, and those 3 inputs are going to tie into the main, processing unit. And then what's going to come out of processing unit is like the actuators or indicator lamps. So, you design it from that point, looking at your inputs and outputs, and then you look at the requirements, right? The system
Hmm.
scope.
Yeah. Yep.
What's how we're going to actually, or what the customer wants. So now you have that piece of the puzzle. And for me, when I do my designs, I always do it from that system block diagram, like how things are going to be laid out. And once I have that, now I can get into the specific interfacing methods I'm going to use to, look at the signals that those input devices are producing, and then how the processor is going to handle it, and then what's the output signals. If I'm going to use, like, if I'm looking at 120-volt actuator, I
Hmm.
need an output module that has a triac, and then I need to know what the load requirements are, meaning how much current that triac needs to source to that actuator. Then I can select the right actuator that has the right sourcing current capability.
Hmm. Yep. Yeah, it does kind of feel like in this, like the scenarios you're talking about here, it's almost like you're, like you said at the beginning of the show, you're trying to make sure that engineering courses have these real world examples. But it seems like in this case, it's like you're just starting in the real world, because you're already talking about specifications based on like real world, like choice of hardware and things like that. And it feels like it's just, I mean, that made me feel like I was on the design floor, like the design at the factory floor kind of thing. And you're like just talking through specs about what do you need with a factory manager, that sort of thing.
Oh yeah, yeah, and that's important to bring the real world into the classroom. It's funny, today, I teach it's called blueprint reading for manufacturing. Of course, they don't have blueprints anymore.
Right. First thing you do is open Adobe Reader.
Yeah, right, exactly. It's all digital based, man. It's funny, like
Yeah. Yeah.
blueprint. I don't know who came up with that, but anyway, I had to kind of, let my learners know, like, hey, back in the day, yeah, they used to
Right.
have, blueprints. It had the blue, but now we
Yeah.
live in a digital age, and even the book that we
Yeah.
have is called print reading. Okay, print reading
Oh,
is
okay.
more appropriate. Okay,
Yes. Right.
so I always bring the real world into the classroom, and like print when you teach that class, most of them, not me, but the ones who have taught it, they just go from the book, and it's very dry. It's like
Yeah.
you
Yeah.
learn about lines and dimensions and different views, and
Okay,
that's
I
great.
have a question that is suited perhaps perfectly to you and your experience here. Why, when I look at, okay, so I look at these connector diagrams, and I, in my heart of hearts, I believe that they're trying their darn best. But some of these connector manufacturers, when they do a drawing and they dimension it, and I'm trying to make a footprint from it, it's like it's never like dimensioned off center. Like all I really want to know is like where do I put 0, 0 on my footprint for KiCad, and then like I want to know like how far away is each footprint from that,
Right.
and it feels like it's always dimensioned from God knows where, like I guess the edges maybe, like why do they draw the way they do, Dr. Don?
And that's a good question. And the only thing I can say is it's based on the person's experience.
Oh no.
Like you have datums. So the
Uh-huh.
datum is really looking at what you're talking about, like where is the point of origin? And I'm
Yeah.
like you too. Like for me, the point of origin for all parts is like the center, okay?
Yeah, like I want the geographic center, so like where the pick and place machine's gonna pick up, right?
Right, exactly, but it's not. It's based on how they're actually manufacturing it, and then their datum is going to change that reference point, and it makes it difficult. So that's where
Yeah.
you got to know how to like translate it when you open up a package like AutoCAD, right? You can
Yep.
translate or move that datum to where it's like, okay, it makes sense to me. It should be in the center, but yeah, that's it's just the individual. I mean, I've seen so many drawings, Chris, and I know that's what
I
you're talking
know.
about right now. It's like it pulls your hair out. Like
Yeah.
I wanted to be in the center so I can.
That is such a key point where like I could totally mess that up in my design. And like at a certain point I look at that and I'm like, oh, I could just hire this out. Someone else can do this for me. Like I don't trust myself sometimes, even if I'm at the top of my game and I've had my 2 cups of coffee and whatever, like
Yeah,
I don't
right,
feel
right,
I
right.
don't feel like it's gonna go well, just because of the history.
Yeah, and I think it goes back to experience. Also, something that I realized based on this conversation, a lot of times the designer is so overwhelmed with work, and the ideal of that particular print is really a communication tool. It's like it's a sales marketing tool, right? So you're
Sure. Yeah.
talking to an
Yep.
engineer, and you say, "Hey, here's the dimensions." And there you have it. It should fit right in your little, spot, like your application. But they don't get into the
Hmm.
specific, like you're saying, hey, I want to make sure that when I do get the model that you have provided,
Hmm.
that center, that reference to what I have, yeah, unfortunately, it doesn't work that way. They'll give you the dimensions, and they'll even give you the
Yeah.
CAD file, but that's where you're going to have to do that translation to move that datum where you want it.
Yeah, I do feel like it's some kind of crossover of like like a connector company is mostly mechanical engineers, and I figured that maybe they're
Right.
tolerancing it because that's what their mold manufacturer has to do, that sort of thing. And
Yep.
at some point, some electro weenie like me is going to go and like be like, oh, how do I put this on a circuit board? But I don't think that
Right.
mechanical engineer cares about it at the moment of drawing, unfortunately.
Jackpot,
So
you hit it. They don't
yeah,
really care.
yeah,
They're looking at it from their manufacturing process, and
mm,
hopefully, the marketing guy or gal, when they go out, they see the Chris Gambles in the world and say, "Hey, I got this great connector for you," and you kind of give them some information. It's like, "Oh, this will do the job," and then once you
hmm
sign on the dotted line, you realize, wait a minute, this the model doesn't jive what I'm trying to do. So you may
right.
have to, massage it, right? You get in there, maybe do some editing and get it where you want it. But yeah, you're hitting on a good point. A lot of times it's the mechanical engineer. I work with mechanical engineers when I was doing product design on
hmm
automobiles, and I had my little body controller module. And it's funny because you know, I we always came late. Not we didn't come late, but they never introduced us to the party first, meaning mechanical engineers,
Yep,
designers, because
yep,
they're
yep.
looking at the sheet metal and they say we need this, this space and this real estate, and then here I come with my little widget, and they start laughing at me. It's like, what's funny? Well, you only got this space to work with. That's it. You
Yep,
can't put any
exactly.
holes in there. You can't
Yep.
deform the metal because the integrity is going to be jeopardized. So good luck. Like, what the hell, man?
Yeah, yeah, exactly, exactly. Yeah, and that's interesting too because, like you said, like there's like at a connector company, it's kind of like how they're communicating. I also feel like there's always priority in terms of like the expertise of that company, right? So, like connector company again, they start from mechanical engineering perspective. I'm sure there's a huge mechanical engineering perspective at automotive companies too, because that's just how those companies started, and they have such an huge outsized impact on the overall piece, final product, right? The mechanical is so critical there.
Right. And the mechanics really aligns with the aesthetics. Like when you talk about the sheet metal, the integrity, one
hmm
thing to say, you can't drill a whole bunch of holes on this surface because now, the integrity, the structural integrity is going to be jeopardized.
hmm
So they'll make the structure where it will handle a certain amount of impact. But now here comes me with my little black box, and it's like, oh crap. It's like, I mean, those
Yeah.
guys really get into the shape. I mean, it's artistry,
Yeah.
but they don't really understand or really don't care. Or maybe I shouldn't say don't care, but we just like, well, no one's
They
gonna
aren't prioritizing.
yeah, no one's gonna see your little box.
Right.
You know
Right.
why? I mean, I've had one mechanical engineer, Chris, he told me like it doesn't really matter. It's like no one's gonna see your box, but it does because as you know, the metal, depending on what the circuit is, if it's an RF circuit, it can actually what attenuate that signal.
hmm
And now, if you're talking about a keyless entry type application, guess what? Instead of having 30 feet, you're
Yeah.
down
Right.
to 5 feet,
Right.
because all
Right.
that sheet metal.
Yep. Yep. Wow. Yeah. I mean, that is one of those. It all comes down to trade offs and like being able to negotiate the. I mean, and like big companies too. It makes it even tougher. I'm sure. What
Oh yeah.
when you were doing that product design level stuff, you were doing keyless and what other kind of designs were you doing there?
When I made a transition from the industrial sector like controls, I started off as a wiring packing engineer, and that's pretty interesting. I think any engineer that's going to get into designing modules, you need to know like the how the wire harness, or in this case, how the electrical current's going to flow, because the ideal behind that is you got a box, and depending on the wire length, you might actually start to attenuate some of the signal, especially if it's something
Mm,
critical. My
sure.
stuff wasn't, I shouldn't say wasn't critical, but it wasn't like an engine controller. The
Mm,
body controller was an experiment where you took various modules that were the instrument panel, like you had the windshield wiper, you had lighting control, you had audible alarms. They usually package those guys in the instrument panel. So the idea was to help with cafe laws, like gas consumption based on the weight of the vehicle. Someone came up with the idea of, hey, let's do a system integration method where we can take all those functions aka the modules, and put it on one board. Thus, the body controller module was born. So the body controller module had at that time, it had a 68HC11, and you had, all the supporting ICs. Motorola at the time was the key designer,
Oh yeah. Yeah.
meaning manufacturing that module. But my role was to look at it from a system standpoint. So what that means, we had other engineers that were basically having to put or connect to my body controller module because they had those functions in it. That became very interesting because now you get into this conversation of like wetting currents for door lock switches, because you got to have at least like 10 milliamps of wetting current to make sure that the contacts are clean. So, that was one thing I had to do, but I had to work with, say, a product engineer that had a door lock switch, and kind of work with their specifications and then do the integration. So ultimately, and I even have the document in my lab here. You got all these pages and there's subsystems, but the subsystems have circuits. So from there, you got this massive integration, and the module is pretty small. It's not like a huge, gigantic
Mm.
module. It's in a plastic case.
Mm.
It's got the male header connector, and you make everything with the female connectors. But the ideal behind that was, again, let's put a box that can communicate with other boxes. So that's where the CAN bus came into
Right.
play, because CAN is control area network, but that was really industrial application method of
Right. Right.
communication. But then someone, meaning the automotive side, decided, hey, if you can use it for industrial applications, why not an automobile?
Mm-hmm.
Because Chrysler had their own proprietary system, and it uses a twisted pair differential means of communication, and it was based on biasing. Like whoever sends the message out first, it had a different current characteristic, and that module will get precedence over the other ones. So you had to come
Oh.
up with this architecture of, who can get the bus at the time when it needed. Okay, almost like
Mm-hmm.
time sharing in an
Yep.
automobile.
Yep. Yep. Yeah. So this, we were actually just talking about, Dave and I were doing, we did a show yesterday of this recording. We recorded it late, but we were talking about wire harnessing after harnesses actually, and just like, well, to be honest, how little we knew about them. I mean, and it sounds like that's pretty integral to this type of work that you were doing. I mean, what was your experience with, like, did you have control over what actually was going onto that wire harness when you were doing these designs, or was it kind of like you were then working with like a endpoint that was already given to you?
I was working with the product engineers, meaning, or at that time they call them release engineers, that were, like you had one release engineer that was, all they did was they looked at door switches. So they
Mm.
became like the gurus of door switches.
Oh wow.
You'll have someone that did like cigarette lighters, and cigarette lighters are pretty interesting. Meaning at the time they had a little glow ring. That I learned a
Hmm.
lot about that, about hot spots, and how
Hmm.
to how those designers look at the optics and make sure that it got.
Do they put those in cars anymore?
I don't know. I don't think so. No,
I
no,
don't.
no.
I think
No,
they
right.
just put the ports now, right? Because it's like everybody made those 12-volt
Yeah, yeah.
adapters, right? But they
Right,
never. Yeah,
exactly. Right, right. But back in the day, yeah, man, they
yeah,
had a
everywhere.
little
I remember them.
it was yeah, it was pretty cool. You had a little glow ring, right? Little optics,
Uh-huh.
and you had the little 12-volt bulb, and it will actually, illuminate that ring. But the problem was it had hot spots, so they had to figure out that. But yeah,
Mm.
doing the wire harness packaging deal, that was really an entry point for me to get into like the electromechanics, because I was, getting involved with switches, and all of a sudden they knew I had a background in circuits. And the guy that brought me on the team, he was a ham radio operator. The guy was brilliant,
Uh-huh.
but he was an
Yeah.
asshole.
Oh,
He was just he
man,
couldn't he couldn't get along
that's
with his people.
that sounds like ham radio operators in a nutshell.
He was brilliant. The
Not all of
guy
them.
was
Not all of them.
like, and, and he would like berate the team in front of the suppliers, and they
Oh
kind of looked
boy.
at him like, what's going on here? He
Yeah.
never did that with me because I wouldn't let that happen, but it
Hmm.
was just a point. We had this mutual respect. Like my hobby was electronics, his was electronics, but he was in ham radio, so he really liked what I was doing and appreciate my knowledge, and I was learning a lot from him. And we did some cool designs. But yeah, the wire harness was my entry point to vehicle systems, and I got into, like, say, electromechanical components, and then I moved into the electronics, which I really wanted to do, and that's where the body controller
Yeah.
was a good lessons learned for me. Yeah.
Yeah, that sounds awesome. I mean, and like the just the integration size, I feel like, we were talking about like just how many circuit boards are on modern cars, but even a couple years back, it was just there are so many subsystems regardless. And like you mentioned, there's so many subsystems that they started to push them into one thing with the body controller module. It's just like it seems like a really just complex system.
Oh, it is. It is. I've got, let's see, I'm looking right now on the top shelf of the bookshelf, where I actually, like I was doing, again, education was always with me, right?
Hmm.
So I would actually collect some of these old modules and I'll make like little stands, like display stands so I can show like how the electronics has evolved from my perspective when I got involved in it in like I'd say probably the mid 1990s, like 95,
Hmm.
96, because I was working on a Grand Cherokee at that time. So I got a lot
Oh,
into,
cool. Oh, wow.
yeah, yeah. And that's when this engineer, he was the senior engineer and he embraced my ability. So I was actually developing some prototypes, which was a lot of fun in a garage. But yeah, that integration is important. So I have all these modules showing like before and then after, and the after is just here's one module, but before you have several modules, right?
Hmm. Yeah.
And that's because cafe and weight requirements and gasoline emissions and you know fuel efficiency.
You said that earlier. I don't know what cafe means. What is cafe?
It's a standard that relate, and I'm trying to remember the acronym, but it relates to, let me see, California Air fuel
Ah,
emissions, CAFE.
okay. Okay,
Yeah.
cool.
So it was based on the weight of the vehicle and how that can impact fuel economy. So
Mm,
if you had like a wire harness, which we actually did this. This was great. We're looking at the door mux, and the door mux is basically eliminating a lot of wiring because you had individual switches, which you do. But what you've done is you actually have a module that reduces the amount of weight because you can have within the module itself a microcontroller, and now you set up this little network.
mhm.
Okay.
Yeah.
So instead of having like three wires that goes to a switch, you can maybe like narrow down to two wires. Okay. And I'm kind of exaggerating there, but the
Sure,
idea
sure.
was you saw this weight reduction, and that played an important part of the cafe standards, definitely for, California, but also it impacted other states in terms of fuel emissions
Yeah,
because
kinda
back then,
everything follows California, right? Just like they drive the
yeah,
standard
yeah,
and
they're the worst case, right,
yeah,
right,
right.
right,
Hmm.
right, they're the worst case. So I had a lot of fun back then.
It doesn't seem like that would like the wiring harness would make that big a difference, but I guess when you really add it all up throughout the whole vehicle, like that much copper, you really probably could start to take it down quite a bit, huh?
Oh yeah, yeah. Like, again, when we did the exercise with the door muck, we had this massive wire harness that was going through the door, through the pass through to through the passenger compartment and the
Mhm.
driver's compartment in particular. It was a massive like bundle of wires, but when we did the door mucks, man, we chopped that guy down like by half. And I mean,
Oh,
literally,
really?
we
Yeah.
did a prototype. We made our own printed circuit boards, and as we started to put our module into the door and we were pulling out the old harness, we saw the reduction in
Yeah.
wiring because we were using a communication bus. That really
Right.
helped because we can
Yep.
communicate from the driver to the passenger side. But if you didn't have that, you got to run those wires from one side of the vehicle, meaning the door, meaning the left side, to the right side, and you got this massive amount of wire harness. And there's weight. I mean, when you pick it up,
Right.
it's like, wow, this
Yeah.
this is
Right,
some
right,
weight
right.
here.
Right, and then times every function that's out there. I guess, yeah, the left, right kinda stuff.
Exactly.
And, like, Cherokees aren't small
Right.
vehicles either, so that and you have to go kinda up and over as well or down and under or some way
Right.
across, right?
Right.
Yeah.
Right, right,
Hmm.
and you have to go to the engine compartment.
Mhm.
You may have to run the wire along the side rail on the floor pan back to where maybe you got your fuel sender unit. So the method of, okay, the harness is like your veins and it's
Yeah,
sending
right.
information, electrical information, but there's got to be a better way to do it, and that's where looking at the control air network or CAN bus was really significant to that because
Mhm.
now it's a messaging scheme, right? And based on how the protocol, meaning like your bits, you can send that over the CAN bus. And instead of, like I say, having massive wires to look at every switch, there's a message associated with every device. And when it sees that binary bit pattern, it knows like, oh, the doors like are unlocked or the windshield wiper is running. Okay.
Hmm. Yeah.
And there was a couple of smart people that came up with that. I was amazed,
Hmm.
like, wow, how did they
Yeah.
do
Yeah.
this?
Right.
And they had this massive book that we had to use to actually validate all the electronics in the vehicle, looking at the messages, and they had some diagnostic tools that they developed where we can look at the message was basically a hexadecimal message,
Hmm.
but you can actually decode the message if you had an oscilloscope, which I did, and it was pretty cool because you can actually see like if the door is locked and at this bit position because it was 8-bit message that it should be a 1, then if you put the scope on it, if you press the switch, you'll see that 1 at that
Yeah.
particular
Yep.
bit position,
Yep.
and it's like,
Yep.
wow, that's pretty cool.
Yeah. Yeah. That's like the car hacking folks too. Like if you go to like DEF CON, the car hackers,
Yeah,
they'll go and reverse engineer canned messages and lim messages and
right,
stuff like that. Yeah. Hmm.
exactly, yep.
You had mentioned blueprint reading as a class you teach, but like in the case of like that wiring harness, what does that drawing look like? So like if you were gonna sit down and be like, I want to know how the left side door switch or the left side door up down for the back side right side passenger window is connected, like what does that drawing look like?
The drawing is going to basically consist of the connectors,
Hmm.
and it's going to show not the individual wires, but it's going to show the diameter of the bundle that branches off the main
Oh wow.
wire
Okay.
harness, and
Uh-huh.
it'll have the dimensions like the length, the diameter. But then it'll show the connectors on there because we work with Packer Electric. They were our connector, for GM. They were the key supplier of all connectors, and they start branching off to other automotive manufacturers. But yeah, they will actually have all the prints related to the connectors and the pin outs, everything you need to actually take the connector apart, replace it. They had special tools because the pins had like little barbs on
Yeah.
them, the
Yeah.
actual
The
pins, and
crimps. Yeah. Yeah.
yeah, and
Huh.
they had a crimp. They had tolerances on everything. Okay, because
Sure.
the vehicle is a dynamic moving machine. So if one of those connectors, and I've seen it where one of the pins in the cavity of a connector with the right amount of force, it can actually push out of that
Hmm.
cavity.
Yep. Yep.
Therefore, the mating pin, meaning the female, won't mate with the male. So now you got this, intermittency, and it's all based on that, that pin not meeting the crimp requirements or the force requirements. So that's basically, yeah, a wiring harness diagram will just show, at least the ones I have looked at, they will just show the bundle size, like the wire routing. They'll show
Hmm.
that. Like for doors, you got to make sure you got a service loop, really for all wire
Yeah.
harnesses. But they had like a drip loop because one thing they discovered, which is pretty cool. I don't know if you've ever done this. The door has a shower curtain, as they call it. It's a piece of plastic that fits over the sheet metal.
Oh,
What
I didn't know
that
that.
does is like condensation, right?
Uh-huh.
So you have to have this drip loop so that the water will, basically flow in a direction where it's going to basically drop at the bottom of the door frame, as opposed to like running down the harness and then getting into a connector, and then you got, bad problems. So
Yeah. Yep.
it,
Yep.
it was really fascinating to learn about wire harnesses. Like if you grab a wire harness, it has this natural tendency to want to form in one, like, well, form.
Uh-huh.
So we had
Right.
to basically not fight the wire harness, if that makes any sense.
Right.
Yeah,
So you have to like
yeah,
kind of
don't fight
design
the wire
around that or
harness.
design with that in
Yeah,
mind and like, yeah, put it the
yeah,
bends where the
yep,
bends want to be, that sort of thing. Huh.
exactly. It's like the wood grain, right?
Yeah.
You
Right. That's
don't
good.
cut across
That's like,
the grain, right?
yeah.
Same thing with wire harnesses. If you fight it, it's not going to give you those, like the service loop. It's not going to have the right service loop, the
Hmm.
length, or like I say, that drip loop. It's not. It's just not going to work.
Yeah.
It'll just cause all kind of problems.
So how did you go from, so you were in doing design and stuff like this, but then you've gotten into the education side of things and you're Dr. Don, you have your PhD in
Yeah, yeah.
education. What was that? What was that switch over? How did you start doing that?
Well, education was always with me. I mean, my mom told me this. I'm laughing now because it's like, yep, I'm in the right spot. Uh, she told me this. She said, She it was a parent teacher conference, and teacher wants to see her, and I didn't know what it was about. I think I was like in the first, second grade, but anyway, had a parent teacher conference. She came back, and she had this look on her face. Now she wasn't mad. It kind of had like a smile, but it was like, I got to be stern here. But what she told me was that while the teacher was in front, showing kids how to read, I was in back showing kids how to read. And the teacher heard me, right? And she's
Ah.
like, that's cool that, I know how to read, but that, I was disturbing the class, right? And, my mom just said, hey, kind of chill. That was really
Mm-hmm.
like the beginning of me being where I'm at right now. But the whole idea of picking up these skills and showing people like the passion of, making stuff, electronic circuits. I was doing woodworking, just making stuff, man. Just
Yeah.
constantly like, hey, here's something that doesn't work. Guess what? I'm not going to throw away. I'm going to repurpose it. I'm going to make it into a little robot or some type of little, device, right? I'll put it in a little pill container, whatever, and I'm off to the races. So that was, like just thinking about it right now, reflecting, that was really the starting point for me where I'm at right now. So wherever I worked, I would see all these, like modules and components thrown away. And I remember I asked the manager when I was working at GM in their tech center in Flint, Michigan. I said, "Hey, what are these modules going?" And she said, "Well, we're going to scrap them." I say, "Scrap them? These will be great, educational tools to show kids about electronics and get them, interested in the work that we've done." And she said, "Oh no, because it's proprietary." And I'm like, "Well, what do you mean?" And
Right.
she said, "Well, maybe one of the kids' parents work at a competitor and they can like reverse it." And I was like, "Okay, that's all right." So, they would shut down like the IP, like they think people are just gonna, like, oh, we're gonna, make our own connector business. No, I was looking at it from the standpoint of the fun, the learning, and also filling the pipeline. That's
Mm-hmm.
important, right?
Yeah,
They do
totally.
it in sports, they don't do it a lot in engineering technical fields. That's why like Dean Kamens of the world with first
Mm-hmm.
competition, it's like we got to replenish this skill set, this knowledge base, because
Right.
if not, that's where we're at right now. As you see, our competitors, foreign competitors, we showed them some things, but they surpassed us
Yeah.
because they believed in what? Education.
That's right. Yep. Yep. Yeah, it's definitely an important area of focus if you want to have future growth. You can't just glide based on past stuff. You have to, it's like continual reinvestment type of thing.
Right, right, right. So that was always with me, just
Mm-hmm.
I would do like at the community center. I remember I would have these Saturday workshops. They were like Saturday enrichment programs for adults and kids. And I had one that was called electricity and robotics. So they bought like a Radio Shack kit, and they learned about electricity, but I'll show them how to wire up to motors. And I had like this Tandy 100 computer, and I was showing like, okay, if you know
Yes.
this, then you can actually
Yeah.
do some interfacing stuff, right? So I
Mm-hmm.
was doing demos with that, writing basic programs, and just having fun, but showing people, particularly the kids, because they, the parents didn't squawk. I say, hey, they need this kit with these parts, and guess what? The kids had the parts in the kit, and we
Mm-hmm.
just had a great time. So,
That's great.
just again trying to share some knowledge and the passion that I have in engineering, electrical engineering, and just making stuff, and that's always been with me. So,
That's
yeah.
great. That's great. And so you are teaching now. What is, so you mentioned the blueprints course. What are the other kind of things that you teach
Oh,
both at
okay.
Jefferson State, but then also online as well?
Okay, so I teach electric circuits one, which is what they call DC electronics. So it's the fundamentals about resistors and LEDs and series parallel
Uh-huh.
circuits. But what I've always done is I always like to talk about the application stuff because I think that's
Yeah.
important. What I'm
Oh, totally.
seeing is a lot of engineers, and I've talked to engineering professors. They say, Don, these engineers, they don't know how to make like a flashlight circuit.
Yeah, right.
You know,
Yeah.
yeah,
Young
it's like
Young
really
Chris agrees. He's nodding his head and saying, "I had no idea how to do that."
right.
Yeah.
So those skill sets are neat, especially in industry, because my industry partners, like we have an advisory board or advisory committee, and they come in periodically. We have meetings like twice a month, or I might go out there, or they might come, to the facility and talk about, some of the skills that they're looking for. Because right now everyone's looking for like industrial maintenance technicians,
Oh,
and that's
really?
kind of like the big, yeah, like maintaining the machines, right? The robotics, the mechatronics based stuff. The welding is at a minimum. They have welders. Welders is like, oh gee, you
Huh.
talk about career tech education.
Huh.
Welders are like number one because infrastructure, right?
You're
Making
right.
new plants, buildings,
Hmm.
maintaining, making jigs, test stands. The welder is like the one of the hottest areas that the state of Alabama is promoting, and it's really international, but
Hmm. Yeah.
mostly in the southern states. But the industrial maintenance is huge because they're saying we got all these automation systems and we need, the technicians to be able to maintain them. So, the circuits, DC is one. There's a electric circuits two class that deals with AC. So you understand about what I call like the anatomy of a sine wave. What does it consist of?
Hmm.
How do you calculate VRMS from peak to peak to peak
Yep.
voltage, phase angles? You get into the trigonometry now because you got reactive elements like inductors and capacitors. So you got inductor reactance and capacitor reactance. And I was just doing that last week with one of my students. He's actually a electrician that works at US Steel, and the guy is like he wants to learn, like, hey,
Yeah.
can you show
Yeah.
me this? So it was just me and him in a lab, and it was great. We got this lab boat system and we're doing analysis. I'm showing him how to take measurements, and it was just great. So I do that. I teach the introduction to robotics, and that's where we got some ABB robots. They learn about how to program. But what I've done is, since COVID, and this was even
Right.
before COVID, I say, wouldn't it be great if they can actually do home-based labs where like some of my learners, and I go between learners and students. So what's a learner? A learner to me is lifelong. You're constantly like learning. A student to me is like just temporary, right? And when I
Yeah.
was getting my doctorate degree and my master's at Capella, they say you're learners, and it just stuck with me. So
Yeah.
that's what it is. But the home-based labs, the kits. So I'll say, hey, buy this Arduino kit, and I'm going to make some labs. There might be some labs that come with it, and if you miss, you can still play at home.
Hmm.
I'm taking the phrase that Dave says.
Hmm.
Hey, kiddies, you can play at home, but they can. They
Right.
they can
Right.
play at home.
You keep things going, and you keep exploring and trying other things too. Right.
Yeah,
Yeah.
right, right. You're in the comforts of your home, and you can add to it, right? Because the kit, about kits and electronics. You just keep adding and adding and adding, and it just grows into this wondrous, learning experience. But they're gaining these skills that companies are looking for, technicians and definitely like engineers.
Yeah.
They're saying that like, hey, engineers, they're great. They can write very good, software algorithms. But if you ask them to design, a light bulb circuit, they're like, what's that? You
Yeah.
know?
Yeah. So
So
is there any focus, so like in this kind of specific thing where they're looking for like industrial maintenance type thing, is there like, are there any courses about troubleshooting? Like where does troubleshooting kind of fall
ah
in this
I
arena?
well, I'm teaching that class. It's called automated system diagnosis and troubleshooting.
Okay. See, now I'd like to take that class, I think. I think that would be my jam.
So here's how that works. We have this Megatronic system that Amatrol makes, and it's a pretty nice representation of what you'll see in an industrial environment. It's got a FANUC robot,
Oh yeah.
and basically what it's doing is making this little pneumatics valve. Okay,
Hmm.
so you put one like the body of the valve on this turntable, and then you push the process button, and then you see everything working, right? You see
Okay. Sure.
they got little pneumatic robots, and it's got proximity sensors, and so it's going through these different stages, and it's actually assembling this little pneumatic valve. So once it gets to like close to the end, the robot, the FANUC robot, has been programmed for one specific task, and that is to reposition the the little body of the valve because there's like a little plunger. So if you can
Uh-huh.
imagine this, it's got a body and it's got ports like holes, and then
Okay.
there's a spring, and then what goes inside the spring is the plunger, and there's a little knob. So if you press on the knob, the spring will compress, and actually what's
Hmm.
happening is the plunger is really a bobbin, and it's blocking the port. So if you're putting
Got it.
air,
Yep.
say, yeah, it'll block, and if it releases, it allow the air to go the other way, right?
Yep.
So that's what this device is making, and it's got a plastic body and it's got a metal body. So the robot is going to reposition it so it can finish the process of adding the little button, okay, for the plunger. Then it moves on this little conveyor, and then there's another little robot, and it's a pneumatic based robot. It'll actually grab that part, and then there's a proximity sensor. So the proximity sensor will basically determine, it's like a sleight of hand magic. It knows where to put the metal parts, meaning the metal valves, on this little chute. It's like a little slide, if you will, that will separate all the metal pneumatic valves from the plastic pneumatic valves, but it's based on the proximity switch. So it's really detecting, like, you got inductive and capacitive proximity sensors. It's really
Hmm.
looking at
Hmm.
the metal proximity, or excuse me, the metal valve. So if it sees that, it knows it goes in one bin. If not, it'll go in the other
Aha.
bin.
Okay. Cool.
Yeah, so this little robot would just do that. It'll just move it like, oh, oh, that's metal. Put it on, like the left hand side, and then if it's not, it'll just put it next to the left hand, like in the middle. So you got all these little bins, and it'll just make production, if you will.
Hmm. So is there like a troubleshooting piece of that though? Like
Yeah,
is there
yeah.
like a systematized troubleshooting thing? That's what I'm always curious about. Like how do we teach? So like teaching design is one thing, and I think that kind of takes there's like the fundamentals for sure, like you said, like circuits 1 and 2, AC DC, all the stuff in there, understanding how electricity works. Like
Hmm.
when I think about like my own how actually learn to make things, I think it's kind of like I kind of wish there was more of like the doctor method of like the watch do teach kind of thing, and like
Hmm.
and so much of that is so hard to systematize. I feel like, and I'm wondering
Yeah.
if maybe you have cracked that code.
Well, the way that mechatronic system that is described, each unit can be separated.
Okay.
So when I got my Siemens level one mechatronics instructor cert,
Hmm.
we had all the instructors, and what happened was you can take those sections apart. So you got like a turntable, you got a sorter. So based on the system that you have, you can individually separate these parts, and there's a PLC. So
Hmm.
the PLC is
Okay.
actually controlling the main rotational linear actuator type device that's on that section, and you learn to troubleshoot based on that. Like, they'll give you the wiring diagrams,
Aha.
they'll give you
Okay.
system block diagrams, and then the instructors will actually put bugs in there. And as a team, you'll
Got it.
start to do these systematic checks, so like check continuity, do some voltage checks, maybe do some current measurement checks. Test out the PLC. Like, do you see the signal? You can force the outputs on or off. You can actuate and see the input switching because the indicators are turning on, the LED indicators. So you start to learn this method of troubleshooting.
Got
And
it.
for me, it's always left to right. Like, you
Uh-huh.
read left to right.
Yep.
So you got the source, you get into the input stuff. There's a processing unit, you look at that, and then you come out to the load, which is being driven by some type of, in this case, controller, transistor driver, whatever, and then you check the load. So that's how I learned to troubleshoot when I, went to Henry Ford. It was always left to right, but some people will like go from the load side and then go in to the power supply.
Hmm.
So
Yep.
if you do one or the other, the key is to be consistent.
Yes. Yeah. Okay. All right. That's great. That's great. That's great. Yeah, and so it does sound like there's like this kind of industrial. So we've been talking about kind of the PLCs and the industrial focus and stuff like that, and we've also talked about some of the home kits you mentioned and stuff. And so one of the things that I had alluded to is I wanted to ask you about was kind of the role of programmatic systems in these environments. So like you had mentioned like the industrial computer versus the controller, but really like my question is there a is there a paradigm shift happening where you see more computers and like Arduinos and processing elements like that on the factory floor in industrial environments versus a PLC, or is the PLC just reigning supreme still?
It's still raining. It still has that president's crisp, and the reason
Hmm.
is you have traditional technicians and the maintenance supervisor, so
Hmm.
they're comfortable with it. So when you mention about the paradigm, yeah, I mean, what is it? Arduino has the, what's it called, the Optia.
I think
their
just yeah,
PLC
Opta.
version.
That's a new,
Yeah,
yeah, the new
Opta.
PLC.
Yeah,
Yeah, yeah.
yeah. I think the rec.
I'd be lying if I didn't say that is exactly what I was thinking about. I was wondering if that's what you think about that, because like and it to their credit, they have ladder logic on there, and it can be either or, but like I was a little surprised by it, if I'm being honest. And but maybe it's an interesting thing for them. Like there's more vision in the space, there's more computing generally, but I didn't think it was going to be the thing that was running the meat chopping machine like we talked about in the early in this show.
Right, right. And see the advantage of using like an Arduino or even like the Raspberry Pi Pico. I think there's some interest in like, hey, we can make it into a PLC. Is the fact that now you have this neural network thing that's happening with artificial intelligence.
Yeah.
PLCs, they're not designed to think like real time. I should, and I'm being very careful when I say this because there
hmm
might be some audience members like, "Whoa, what are you talking about?"
Right.
And the
Right.
reason why, and again reflecting on my experiences and hearing like the technicians that are in my classroom, everything is just pretty much like the traditional way of doing controls. You have a device that is being triggered by say a moving part that's going
hmm
to provide a signal. It goes into the PLC, and the
Yep.
PLC is going to take over do the automation. Meaning you don't have to have this massive bundles of wires. You can basically run everything from the field to the control panel, and then using addressing, which is the slick thing, you can move things around, right? Because
hmm
all the field devices are there. You can go to the field device, replace it, but you don't have to replace all the wiring, just the
hmm
device.
Yeah.
And then
Yeah.
you can do a quick test and then you see it. So now we're talking about using embedded controllers like the Arduino. And this is kind of a segue into what I've been doing with my articles on control.com. OpenPLC.
Okay. What is that?
That now that's a pretty slick platform to learn about programming PLCs. And the way the Opta was evolved, I'm not saying it was like looking at what the creator of OpenPLC did, but they knew like we have a platform that most people know about, meaning the Arduino. They know how to program it, but we're going to get into this industrial space because it is a booming area related to automation. We have the expertise to manufacture the boards. They have their Protina, machine control platforms, but now they're saying let's really get into that industrial control space by making a controller that has the same method of termination, terminal lock, and you can use ladder diagram programming. And now we can
Mm,
really capture that market. It's easy, it's small, it's slim, and there you have it. Okay, so that's kind of like the business aspect. Let's look at that market because it's booming. But see, the secret sauce is, like I said, you can add the artificial intelligence. They got tiny, machine learning. You can
right.
put
Right.
that on there, and now you can transform it. PLCs, it's still. Put it this way, it's proprietary
hmm
because we're talking about an open architecture with the Arduino, right? I mean,
hmm
when they came up with it, it's like, hey, you could make your own Arduino, just don't call it Arduino,
Right.
which is a great thing for makers, right? And you got all these different businesses that are actually developing these shields, which is great. So that's where the line of demarcation is. It's like looking at the true innovators versus we just need to, stick to tradition because tradition worked. But if you're going to be competitive, you have to cross that other side, which
Mm,
Arduino is really challenging. Say maybe the Rockwell Automation, Allen Bradley PLCs that are General Electric, or Mitsubishis or Omrons, okay, because they have these
mhm.
small little form factor controllers. Guess
Right.
what? Arduino came out with one, and I think Raspberry Pi is looking at coming up with their own industrial controller.
Interesting. Yeah, I mean, one thing that I do think about is like when I've talked to people in industry, like some of the other folks that I know in like factory settings and stuff like that, they are diehard. They are like diehard Allen Bradley or diehard, whatever the other brands are, right? And like so that's another potential. Not that that's insurmountable, but it does seem like, and each of those kind of has their own little special flavors and catalogs and ways that they interoperate with other things.
Oh yeah, yeah, and that's the battle. I can remember this was by accident. I had a S7, I think it was like a 1200 series little PLC, okay, and it dropped. I'm trying to remember how it dropped, but when it dropped, I said, "Oh well, let me see what's inside of it."
Mhm.
There's the engineering, the knack,
Yep, there it
right?
is. There it is.
What's
Yep.
it? Yeah, what's inside of it? So I opened it up and I looked at the logic board. Well, they had their own specific, microcontroller. It might have been an ASIC or something like that because they had a
Ah,
Siemens part number.
sure.
But with that said, it was like, man, you could put an Arduino in this plastic case. You can use a 24-volt power supply. You can put all the optocouplers, the transient suppressions to protect the IO. But there's the PLC.
Mm,
There's like nothing spectacular. I was thinking
you're right.
like, wow, it's got to be like
There's still
industrialized.
pins on the chip, huh?
Yeah, yeah. I thought it was going to be industrialized. No, it's like this
Uh,
looks like an Arduino.
yeah.
So it's the if you understand like the specifications of a PLC, one of the big aspects is 24 volts,
Hmm. Yep.
and the current might be at a max like 5.
Yeah.
But then you have to look at the inputs because the inputs, they're switching current. So you got to protect and you use, basically you use opto couplers, right? Because you got 24 volts. Well, the poor microcontroller is
Hmm.
5-volt or
That's right.
3.3-volt compliant.
Yeah.
It can't handle that. So the way you do is you put that interface, in this case, an optocoupler, 24 volts input side, and then the output is going to have, basically you got your open collector transistor.
Hmm.
That's going to provide the low voltage, low current that the microcontroller is like, okay, now I can, deal with this. And it's the
Right.
same thing on the outputs. You got optocouplers and you just do the reverse, right? You pull everything high, you source it, and you got maybe like if you're doing AC, you got triacs. So now you can drive the triac with the low side, meaning being controlled by a microcontroller because the optic controller is like the interface and you're off
Hmm.
to the races from that
Right,
point.
right. Yep, yep. So then how does so like you're saying, like the microcontroller that's running in there is possible to be a wide variety of microcontrollers. Then OpenPLC is a software that basically is that compiling like ladder logic down to something that can be used on a lot of commercial
Yeah,
boards.
you hit it. Yeah, it's pretty fascinating. It'll actually compile to a binary file.
Okay.
But what gets generated out of that is you have like it's based off of the IEC spec. IEC stands for International Electrical Technical Commission. So it's a European standard.
Hmm.
And the specific standard for PLC programming is the IEC 61131-3 functional programming languages. So there's 5 functional programming languages. And some of them are graphical, some of them are text. So you have the ladder diagram, you have the functional block diagram, or which is basically graphical. Then you get into some kind of like Pascal-ish programming structure where, and that's the key word, it's structured text.
Hmm. Okay.
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 And then you have like kind of an assembly version of programming, and that's the instruction list. Okay. And then you have a sequential function chart, which really gets into the behavioral, like you mentioned about sequencing and it's tasks, it's timing, it's time-based diagram. Okay. So
Yeah.
that's graphical. So now with that spec, again, the creator who did this, he actually, I'm trying to remember his name, but he did it for his PhD in cybersecurity. Actually, he went to University of Huntsville, Alabama, and he got a degree in cybersecurity. But I think he did it on control systems, right? Because
Yeah.
espionage. So he
Right.
came up with this platform called
They do
Open.
have a village at DEF CON for PLC hacking as well. Second time I
Yeah,
brought up
there.
DEF
See,
CON
there
today.
you go.
Yeah,
Right,
yeah,
right,
yeah.
right. Did you see the movie called Black Hats with
Black Hats. I don't know if I
Chris
saw that one.
Helmsworth?
No,
Yeah,
I don't
that
think I
that
saw
was a
that
good
one.
movie.
Okay, I'll have to check it out.
Yeah, that was a good movie because MIT grad, right?
Uh-huh.
It's like the MIT people always get in these movies, but
Uh-huh.
they had to tap into his services because he was doing some nefarious hacking, and they,
Yeah,
cut a deal like, "Hey, we need your help while hacking." And it was about, basically using PLCs. They put
sure.
a virus, and they were able to shut down this plant because this plant was allowing them to gain access to some type of natural resource, and they can
Hmm.
make money off of it. Okay.
Well, wasn't that like the Stuxnet thing too? Didn't that eventually, when it hopped through, like the Stux worm, like got all the way through all those different USB keys and then into the IRAN controllers that
Yeah.
were those were industrial controllers as well, I think, right?
Yeah.
Yeah,
Exactly. Right.
yeah.
Right. They're industrial controllers. So with that, that was the whole plot of learning about cybersecurity and
Hmm.
plant
Yeah,
machine to machine control
yeah, yeah.
technologies. But yeah, the open PLC platform, it's just that it was his way of, like, it's open source. Well, not open source, but it's open to the community. Like, the
Mm.
architecture, you see all these files being generated, but actually it'll compile down to a binary file that will go into, in this case, like an Atmega 328. Actually, he's got a series of different microcontrollers. The ESP32 platform is in there. I think he's got like the RP 2040, and he keeps
Okay,
adding more and
sure,
more, right?
sure. Yeah.
And it's just like, now you can make your own PLC. So I use that to do the introduction to programmable logic controls. They get a
Oh,
kit,
nice.
and
That's
I'm
great.
showing them how to program, and that's where the control automation or control.com article, I did a pitch like,
Uh-huh.
hey, this is some good stuff. Would you be interested? And there was more to the proposal, and the uh,
Oh,
the
yeah.
editor, content editor, came back. He said, "Yeah, this is great because it's perfect timing." He said that Massimo Bassani was there, and he talked about Arduino's and PLCs. So he was giving them a clue, like, "Hey, we're going to
Mhm.
move into this sphere, and it's perfect." And he
Yep,
was really
yep.
like looking for the market because EET Tech, that's the marketing venue,
Mhm.
but the magazine, the website is called control.com. They talk about industrial controls and circuits and systems and all that. So when I did that pitch, he's like, great. And I've been writing articles. I think this is my sixth article that I'm doing, and doing a
Oh, great.
series.
Yeah.
Yeah. So
Yeah.
yeah,
Well,
you
yeah,
can
we'll
kind of
definitely
check
link that
that
in
out.
the comments below, or in the show notes below. So there's a lot
Yeah.
of great articles there. That's awesome.
Yeah. Yeah. Thank you.
Wow.
Thank you.
You
Yeah.
Dr. Don, you do a lot of stuff here. So I mean, it sounds like a long career, and you've been kind of going across the spectrum here. We are a little bit past an hour, but what else do you want people to know about you, or things that you've done that people should check out?
Well, here's my marketing ploy. I have a new book coming out next month.
Aha! Awesome. What
Yeah,
about it?
yeah. It's called the M5 Stack Electronic Blueprints book,
Nice.
and that's a fun part. It uses the M5 Stack,
Uh-huh.
both versions, the touch screen and the non-touch screen. But I got a lot of projects that show people how to interface with Arduinos, snap circuits. So if you want to get your kids involved in it, they can learn about
Yeah.
electronics,
Oh, that's great.
Wi-Fi devices, all kind of cool things. So that's coming out. Well, about the conference. Yeah, I got a conference that I'm going to be doing a workshop.
Okay, awesome. I was gonna say we will have a link to the pre-order if the M5 stack book sounds good to
Electronic
you.
Blueprint. Yep. Yep.
Yeah, yeah, we'll
Yep.
have the link to the pre-order. That's great. That's great. I
Yep.
didn't even realize this is like the book tour. You're on the book tour right now, you know?
Yeah, 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 yeah. That's one thing they say is like, make sure
Yeah.
you start promoting your book. So,
Yeah, yeah.
and I got a webinar, design news webinar coming up. It's on what is it? I'm trying to remember what it is, but it's like March, and I'm going to
Okay.
be talking about. Oh, I think it's, yeah, Node Red and how you can use that with ESP32.
Oh, nice. Okay,
I think
that's
that's the
great.
topic. Yeah, yeah,
That's
yeah,
that's a good
yeah.
one too.
So
Yeah, I really like that
yeah,
as like a control diagram. Well, not quite like how we're talking about PLCs, but like as a way to kind of show data flow when you're sending stuff up to the cloud. It can be really,
yeah,
really
yeah,
useful.
yeah, yeah. It's fun. Yeah, yeah. So, and I got three. I got a total of four. So that's the first one, and I got three others that are coming, later on in the year. So yeah, never dull moment. Yeah, never dull moment.
That's great, man. You are everywhere, and everywhere is way people can learn a lot from you there. One question about the design news thing that you do. So you do these design news DigiKey courses, and they're like continuing education credit. Is that like can those can go towards like a PE style like CEC, like for professional engineer?
Well, IEEE is involved in that.
Uh huh.
So the way it works is you got to participate in each of the sessions that you sign up. And I guess over a period of time, when you get that, I don't know what the magic number is, but when you get this magic number, you will get a certificate from the IEEE saying, you met the requirements to receive the certificate. And the cool thing about that, Chris, was one of the participants that took some of my classes, and the guy that got me involved in the embedded online. His name is Jacob Benedico. We're both
Oh yeah.
Michiganians.
Uh
Yeah,
huh.
yeah. The guy
Yeah.
is sharp.
Yeah.
He the guy who got his IEEE certificate, he did a LinkedIn post, and he said, "Hey, I want to thank Don and Jacob for the wonderful classes that they put on." So that's what it means, for me.
Yeah.
Just one
That's
learner
yep.
and an inspiration. That's it.
Yeah.
Yeah.
And speaking of Jacob, so you will be also at the online embedded conference. I
Yep.
forgot the name of
Doing
that
the
one.
ESP
Yeah.
32 IO primer. Yeah. And,
Mm,
and yeah. Yep.
yes. Great. Yeah, and that's another good one. So that's a free conference. People can basically sign up for that. It's all online, and I think it's in April of this coming year, right?
Yeah. Yeah. Yep.
That's
Exactly.
great.
Yep.
Well, there are a lot of great places to go and check out your stuff, Dr. Don. Thank you for being here. We really appreciate it, and I hope to have you back on and hear more about your fun things you're working on.
Definitely look forward to bringing some more fun stuff that I do around the lab here. So yeah, and at Jefferson State. Yep.
Of course. Yeah. All right. We'll see you soon.
All right. Yep. Bye.